That's our first test only for the chapter, so.
Okay.
There's been like
Online can hear us?
3, so
Online folks,
I'm calling this.
giving you a shout out. Can you hear us? Oh, good. Thank you. I'm so happy to see you all. So how's everybody doing? Well, that's- Okay. Anybody with a definite 2 thumbs up? Not so much. Anybody been doing anything fun this summer so far? Already. We only have like about 1 more month. Summer classes, so y'all should be excited, right? Anybody been doing anything fun though? No fun yet? Nobody's gone to the beach? Oh, wow, that's so wild. I always thought that young people like to go to the beach. Anybody been enjoying all the sports activities that have been happening? So much happens in the summer. We've had basketball, hockey, we're gonna have tennis starting. Oh, God, or some of you are
They
looking.
only score like 2 points. So.
Football season, let's see. So yes, all of these meetings are recorded. And you can always find them in Teams. I plan to get you some of your grades this week so that you don't have to all send me messages asking. You will hopefully have your exam 1 grades this coming Tuesday. So it'll be June 23rd. You'll end up knowing your grades before your next exam. So that is the anticipated date for those.
Yeah.
So I will keep you posted on that. Keep in mind that your TAs grade your exams. So if you do have questions about your grades, then your first best bet is to actually contact your TA because they'll know how they awarded points. So that is the best course of action. See your TAs first. Then if you're still having questions about what grade you had or not understanding material, then certainly come see me. So I'm going to ask you two to split up. So one of you will need to come over to another table, please, for me. Okay, so we have some different problems to work today, and you're going to get to work in your teams again today. So you will want to have your game hats on because we will have a little friendly competition today. So make sure that you know how to reach your teammates. How do you reach your teammates? Definite, assured way you can find them. Ready to know? Everybody has their team channels, right? So if you haven't found it already, everybody has been assigned a team channel in Teams. So you can always use that to collaborate with your teammates. So you'll want to do that today for what we've got going on. Okay. Who knows what chapter we're on and we're going to be discussing today in terms of problems?
Chapter 2.
Oh yeah, we're on chapter 2. How many sections do we have for chapter 2? Yeah, we've only got 3 sections for chapter 2, and then we'll have 3 sections for chapter 3, and those will be the 6 sections that will be on your exam too. So you definitely want to make sure that you are aware of what content we're going over. Okay, so we're going to get started with our different problems for chapters 2.1 through 2.3, and then we'll get into some teamwork, and we'll see who wins. So let's go ahead and check it out. Who can tell me what chapter 2 is all about?
Determinants.
Yeah, it's all about determinants. They really focused a lot of their attention on determinants. So we are going to be going through these. You will want to know how to calculate a determinant in several different ways. So from chapter 1, can anybody tell me what was the primary way that we calculated a determinant from chapter 1? What kind of matrices were we dealing with? And how did we calculate those determinants?
2x2 matrix.
It's a 2 by 2, and we had a simple equation for that, right? So not too bad. Now we have to get into the fact that we are going to be looking at bigger matrices. Let's see. So we also, in chapter 1, we did learn how to find the inverse, right? Matrices. What kind of matrices can we find the inverse for? Yeah, definitely square, right? Yes.
Yeah, 2x2 and 3x3.
Yeah. So what was the method that you learned for the 2 by 2? Anybody remember? We have the equation for the determinant for a 2 by 2, which was what?
AD minus BC.
Yeah, it's just AD minus BC. If we do the inverse of a 2 by 2 matrix, what do we then have? If our online folks. Anybody remember? So for a 2 by 2 matrix, and we want to find the inverse, anybody happen to know that particular equation? Mhm.
D, negative B, negative C.
Yeah, so the D and the A were switched, and you got negative B, negative C inside our matrix. Yes, so then we can also find an inverse of a matrix, a square matrix. How did we do that? Yes.
The identity next to it.
Yeah, and what do we call that? Remember what that was? Called the inversion algorithm, where you put the identity matrix on the right-hand side, you go ahead and reduce them both together, and you end up with your inverse on the left, or on the, let's see what we got. So then, so chapter 2, we are looking into now determinants by cofactor expansion. So we can find determinants in a couple different ways. So who can tell me about cofactor expansion? What are we doing with that? What are some things we have to remember? Cofactor expansion.
It has to be a square matrix.
Yeah, we've been dealing definitely with all these different square matrices, right? So that's something that's really good to remember. You always want to know what are the dimensions of the matrices that we're talking about, which size do these theorems apply to. So we are looking at cofactor expansion. So what are some terms that we want to know for cofactor expansion?
Minor matrix.
Yeah. Ooh, I like it. So we've got a minor thrown out there. So what is a minor of a matrix?
Out the row and column, either 2 by 2 matrix or whatever's wrong.
Yeah, so we're actually finding with a minor, we're finding the determinant of a submatrix when we've ruled out like a row or a column. And then we have cofactor, which is that one. Yeah.
You multiply the minor by negative
Yeah.
or you can use the 3 because it's the same value.
Yeah, so you can remember that particular equation, or you can remember that checkerboard pattern to figure out your cofactors. So we're going to be looking at that. And then this first section, if we look at section 2.1, does anybody remember any other kind of fun technique to find the determinant? That only works for a 3 by 3 or a 2 by 2? So we have for determinants, we know easily how to do a 2x2. We also now from this section 2.1, we know with using cofactor expansion, that's another new method. Then there was a second method that you could use for 2x2 or 3x3. That was real quick and easy.
It was the expanded AD minus BC where it's like the diagonal arrows.
Yeah, it's an arrow technique. So you do have to be careful about what size you use that for. So you can only do that for your 2x2 or your 3x3. Anything larger, you're gonna have to resort to, unfortunately, your laborious cofactor expansion, unless you happen to know some other cool techniques, and we'll get into that later. Okay, so anybody have any other cool things that they want to point out that you might need to know about determinants from this initial section 2.1? What are some other things they wanted you to notice?
If there's all zeros in like a row or column, then it's gonna have a determinant of 0.
Ooh, good job. So if we have a row or column of zeros, our determinant, we automatically know it's 0. So we can really quickly glance at that.
You can also try to get them as 0.
Yeah. What else did they want us to notice?
Triangles. If you have a triangle, then you just multiply the main diagonal.
Mhm.
You'll get your determinant.
Yep, we've got that one too. That one's a really cool one. All right, so we've got some helpful hints for us. So let's jump into some problems. Let's see if our online folks, let's see what they've got. Yes, so Cody's got some good comments in there. And we're gonna be looking at those with our problems. Okay. So you will want to make sure that you check your course syllabus to see which problems I've listed on there to make sure that you know exactly what you're doing. All right. So we are going to be looking at problem 1. All right. It says find all the minors and cofactors of the matrix A. Oh, that is fun and laborious. So how many should we have?
15.
9
Okay.
plus 9. So
Yeah, we got 9 of each. All right, so let's see here. All right, we're gonna have a friendly little individual competition. So we're gonna go ahead and see how fast each of you can calculate all of those.
which one are we doing?
We are doing problem 1. So all those the fastest. Got them all? Okay. So what's M13?
27.
Okay, C13? Okay. What is M12?
21.
21? C12? Okay. What is M11? Okay, what's C11? Okay. All right. What is M21? Okay, what's C21? Say 11? Okay. All right, what is M22?
13.
Okay, what about C22? Okay, what about M23?
-5.
What did you say?
-5.
-5? All right, how about C23?
5.
5. Okay, we got one more. So we got M31,
-19.
-19. C31,
-19.
okay, what about M32?
-19.
-19. About C32,
19.
okay. And then we have M33,
19.
19. And how about C33?
Also 19.
Anybody have any different numbers? Everybody get the same thing? All right.
What are we looking at?
I'm sorry, we're doing 1. Problem 1. All right. So let's see if you are correct, sir. So let's check it. Okay. All right. Ooh, we got M11. You told me C11 was 29. Okay, you told me M12 was 21. Ooh, I had that you said C12 was also 21. But it should be
-21.
-21. Why is that? What position would this be in?
Because of the grid. It's
Yeah. So you can always tell whether or not they're going to match, right, by our checkerboard pattern. Or if you're raised here to an even or odd exponent. So be thinking about that. All right, so M13, you told me 27 for both, good. Okay. Then M21, you told me a -11 and 11, good job. M22, you told me 13, and then C22 was 13, awesome. M23 was -5 and 5. M31 is -19. C31 was also -19. Ooh, so that one you had told me they were both the same, yes?
Which one?
Or sorry, you had told me that C31 was 19. Okay. M32, -19. C32 is 19. M33 is 19, and C33 is 19. All right, so I have that you missed 2 of those. They just needed the opposite sign. Anybody get them all correct?
Checked.
You what?
Checked it, unless I'm like looking around.
Okay, so just keep that in mind. Want to make sure you keep that checkerboard pattern. Okay, so those are the answers for those. So does anybody have any issues with how each of these are solved? So for instance, this M11, where did we get this M11 from? What is 11 referring to?
column one.
Yeah, exactly. This spot right here. So what are we doing? We're forming a sub-matrix by crossing, if we're designating this as our entry that we're looking at, 1, 1. We're going to go ahead and cross out the row and column that it's in, and we look at this sub-matrix that's left over. So we've got 7, -1, and 4 left over. What do we also notice about the notation here that's different? Anybody notice anything?
Oh, there's absolute values.
Yeah, so here it's changed. Here we have brackets. So just realize if you have these brackets, you are signifying to someone that, hey, here I'm talking about a matrix. When you happen to have these parallel lines that look like absolute values, here you are signaling that you're calculating the determinant. So here you're calculating that determinant of this submatrix and you get 29 here. So you basically follow that same pattern for all of the rest of your entries. So it's a lot. Okay, so let us go ahead and jump to 3. So we're just going to look at 3A. So here they're asking for M13 and C13. So which entry are they wanting us to look at?
1.
Yeah, they want us to look at this one. So what are we going to do? We're going to go ahead and cross out this column that the 1 is in and the row that 1 is in. You're going to be looking at that submatrix that's left over. What is the size of the submatrix left over?
3 by 3.
Yeah, it's a 3 by 3. Okay, then what do you think? What might be a very easy technique to then do? Anybody have any suggestions?
Take the top row of the 2 zeros.
So this was another really important point. So we're going to go ahead and look at this. So here we're left with, this is our submatrix 0, 0, 3, 4, 1, 14, 4, 1, 2. As you astutely picked out, you're left with a 3 by 3 matrix. We have to continue to simplify that and to find our determinant there. So you wisely chose, let's go ahead and use cofactor expansion along this first row. Why do we want to do that?
Let's work.
Yeah, it's a lot less work. What do we notice immediately? It's got 2 zeros. Zeros are our friends when we're calculating determinants, as long as what? So you always want to notice your zeros. What do we look for if we see zeros in a matrix?
All zeros.
If it's all zeros in a column or row, what does that tell us immediately?
It's going to be a 0.
It's determinant 0. But if it's not, then our next best thing is to recognize where do I have the most zeros, because that's going to simplify my work for calculating that determinant. So here we went ahead and we do cofactor expansion along that first row. Both of these first two terms here are going to end up being 0. So I really only need to look at this last term. And then this you know how to do easily. How would you calculate this determinant in that 2 by 2?
Last one. So be 0.
It's going to be what?
0 anyways.
Yeah, so these two terms are going to drop out, right? There's 0 times this, 0 times that. Then how do we easily calculate this? This should be like burned in our memory, yes.
Proportional columns, because you could just multiply the 1 by 4. So that gives us it's equal to
The
0.
determinant is 0 because they're
Yeah,
proportional.
yeah, exactly. They're proportional by a factor of 4. So you'd immediately recognize that too, right? So there's lots of patterns to notice with all of this. Okay, great job. All right, so obviously you would go on and you would look at that same thing for your other different minors and cofactors that they might choose. All right, let's go ahead and we'll look at number 11 because we have some interesting points we want to know. Okay. Ooh, number 11. This one is the arrow technique. So here's the next one. I want you to see if you can solve it. What was your name, sir?
Joshua?
Joshua and?
Jose?
Okay, so Jose and Joshua. They did a good job in leading us off on our last one. let's see who can do number 11 the fastest. So here we're looking at number 11, but look at what they're asking you to do. Ooh, the arrow technique. So we're looking at problem 11. Dun, 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 dun. They want the arrow technique.
Can I ask you a quick question?
Yes.
What's the best way to remember the arrow technique? Because I remember that thing has like a lot of steps to multiplying and adding a lot.
Right, so let's solve it and then we'll talk about it. We'll give everybody a chance to see how fast they can get it. And then we'll talk about that. Okay. Looks like Cody's got an answer. The online section, who's got it for in person? I get an answer for number 11 in here? And hint, you will have a question like this on the exam. I'll ask you for arrow technique.
I don't know if it's right, but I got an answer.
You did? Okay.
I got negative 65.
You got negative 65 too? Okay, name?
Joshua.
Yeah, sorry, no. Jackson? Okay. All right, so Cody for the online students, negative 65, and Jackson, you say you got negative 65 as well. Okay, Jackson, how'd you do it?
I copied over the first two columns to the right of the matrix. And then I added up, or I multiplied the diagonal rows.
Mm-hmm.
I would multiply the diagonal row and then add it to the next diagonal row to the next.
Okay.
And I subtracted it by the opposite diagonals.
Okay, so which diagonals did you do first?
I did the ones that go from top left to bottom right.
All right. Okay, so let's check it out. So good job. Look what we got. So here we have our matrix. Here you are going to replicate your first two columns. So you see how the negative 2, 3, 1, you got 1, 5, 6 been replicated. And then you're going to be multiplying along your diagonals from your top left to your bottom right. So we get negative 2 times 5 times 2, that's going to be your negative 20. And then you go ahead and add up your other ones. So this one would be -7. Then here you have 12 times 6. So basically you would sum up those quantities. Then we've got to subtract what we would get going back the other way. So then now we are doing the 4, 5, 1. So that's your 20 here. You get the -2, -7 times 6. You get your 84. Then you've got your 1 times 3 times 2. That's going to be your 6th term there. You're going to add those all up. Then you subtract those from each other. You get -65. So here's the deal, folks. Why on earth would you use the arrow technique? So that goes ahead to the kind of the question that was before, and I told him to wait. Why would we decide to go ahead and use the arrow technique? What would give us some clues that this might be a viable option for solving for our determinant?
You do it all in one go, I guess. You don't have to break it up into multiple determinants.
Yeah, I would say the math is easier, don't you think? I don't know. I think it's pretty quick. I mean, you're just like, oh, boom, boom, boom. I'm going to multiply these and multiply those. And then this is something you might even be able to do in your head. Any other points that we want to remember about this arrow technique? Why would we choose it?
It works for 3x3.
Yes. This is the technique that works for your 3x3 and your 2x2. So if you happen to see this and you may forget maybe some of your other techniques and you see, oh, it's a 3x3, go ahead and use my arrow technique. Any other reasons why you might choose it? Do you have any other ideas? So when you're faced with these kinds of problems, I want you to first always take a moment to observe your matrix. You want to observe, okay, what size are we dealing with? Then I want you to actually look at the entries in it and see if they provide any useful information for you. Do we have any all rows or columns of zeros? No. Do we have any proportional rows or columns? No.
Probably not.
Probably not. Do we have any other strategic zeros?
So our only option to do that.
So then you're left with, okay, if I really wanted to solve this pretty efficiently and I don't have any other useful things that are telling me otherwise, I think I'm just going to go ahead and use my arrow technique. But this matrix isn't really in a simplified form yet. So that might be my quickest bet for going ahead and solving this. So that's something you want to think to yourself, especially for the exam and you're on time, you have only a certain amount of time, right? Then you might think to yourself, maybe arrow technique is my best friend at the moment. So always be looking at your matrices when you go ahead and do these problems. Okay, let's go ahead and let's look at our next one. We've got 15. Ooh, okay, so let's check out 15. So good job. Thank you, Cody and Jackson. Cody put in an explanation. Is there maybe if there is no zeros in any row? Yes. So Cody, you're right on track there. Yes. So we didn't find anything useful in that last matrix to take advantage of. Let's see. So number 15. Then it says find all values of lambda for which the determinant of A equals 0. So if you were faced with a problem like this on the exam, what do you think you would do? What would we do to solve that?
Take me back to school.
Well, what's involved here? We want to find all values of lambda for which the determinant of A equals 0. Well, luckily it's a 2 by 2, folks. So what do we do? Yes, sir.
Cross multiple.
Okay. So you wanna, what would we be multiplying?
What's the symbol called?
Lambda?
Random? Random minus 2 times random plus 4. Then that is also subtract. Negative 5 times 1.
Good job, yes. But what would we do with that? We have lambda minus 2 times lambda plus 4 minus negative 5 times 1. What do we do with
I
that?
can do high school math.
Yes.
We make them proportional on the top one. So like if lambda is -3, does that make sense? So like,
So if we look at this, they're asking, it says, find all values of lambda for which the determinant of A equals 0.
You just treat it as a determinant, as a variable, and then just do our AD minus BC. And then we have to factor it out, and then we have to get it into its a polynomial form, and then factor it out again to get there too.
Yes, I think you're kind of saying something similar. So what are we setting that equal to solve for this?
0.
0, yeah. Right, because you're essentially, that's solving for the determinant, right? AB minus BC is your determinant. So when would the determinant be equal to 0? You're gonna set all that equal to 0, right? You're gonna solve for your lambdas. All right, so let's check it out. Let's see what our online. Yes, so Cody has used that AD minus BC equals 0. Yes, then solve for lambda as a variable. Yes, that is exactly our strategy. So we're gonna go ahead and do that. So we're solving the determinant of A. We're setting all this jazz equal to 0. Whew. Oh my goodness. What do we get? We get, so here we have lambda minus 2 times lambda plus 4 minus 1 times 5. That's our AD minus BC. You go ahead and expand that out into a polynomial equation. Then you're going to go ahead and solve for your quadratic equation here. We get that lambda plus 3 times lambda minus 1. All of that's going to equal 0. So what does that mean our values of lambda have to be for that to hold true? So if we have lambda plus 3 times lambda minus 1, you would set those equal to 0. What's going to make that true? If lambda equals -3 or lambda equals 1. Okay, so everybody see that? We just set that equal to 0. Solve that equation. Now, who remembers how to solve for your variables? Is this something that you remember from your pre-algebra days, I hope? Yeah, does it kind of ring back bells? Okay, so you'll want to make sure that you know how to solve some quadratic equations there. Okay, let's look at our last one and then we'll be moving right along. Okay, we wanted to look at, I think 19 was our next one. Okay, let's look at 19. It says evaluate the determinants in exercise 13 by cofactor expansion. All right, so let's look at 13. Oh, look at that. So in 19, they're basically telling you which row or column to choose to do your cofactor expansion. But if we just look at 13, I just ask you to solve number 13. What would you do? What are we looking at here, folks? What are we noticing first?
2 zeros.
Yes. So kind of run through your mind. Size. We got a 3 by 3. Yes? Ooh. Do we have any proportional columns or rows? Not that we can tell. Do we have any all 0 columns or rows? No. All right, looks like we're going to have to solve. We could use the arrow technique, right? But do we really, is that really the most efficient? Not so much, because look here, we got 2 zeros in that first row. So then at this point you say to yourself, what are you gonna do? Yes, sir.
Factor, cofactor expansion.
Yeah, cofactor expansion using,
First row.
here we're gonna use our core entry as 3, right? So we're gonna be looking for our cofactor expansion entry using that entry 1, 1. So we're gonna cross out that row that 3's in. We're gonna cross out, all right, anyway, go ahead. You could do the arrow technique. They decided they wanted to do the arrow technique. But they could have done it differently, right? So they could have done what? If you're going to do the math the other way, if you did cofactor expansion, what would our math be?
Times 5 plus 4 times 3.
Okay, so we'd have 3 times whatever was in here, right? So what's our determinant of our little submatrix? -1, 5, 9, -4.
No, that's Deb.
-40,
So we got 4 minus
-41.
-41. All right, so you can see where we end up here with our -123. So just be aware, they went ahead and decided to do arrow technique, but you could have done it probably quicker in your head the other way. You do cofactor expansion using those zeros. So just be very careful when you encounter a problem on the exam, decide what is the best mechanism for solving these. All right, let us go ahead and we are on to section 2.2. So we have some important points to go ahead and make about section 2.2 as well. Obviously, you want to make sure that you take note of your different theorems. Someone already said this, is that we have here, let A be a square matrix. If it has a row of zeros or a column of zeros, we've mentioned already that the determinant is 0. Here they also want to point out that the determinant of A equals the determinant of its transpose. Anybody remember what a transpose is? That'll come back in later. What do we do for a transpose? So some of these, yeah, you switch your rows and columns. So some of these terms you want to have like right at the forefront of your mind. Okay, so we're going to be looking at this. We have some interesting rules we're going to have to remember here. Okay, we also, you guys mentioned astutely, also that a square matrix with 2 proportional rows or 2 proportional columns, the determinant of that equals 0 as well. So don't forget to check for both rows or columns. That's something that people have a tendency to forget, because there might be one there. You might have a relationship that helps you out really quickly. Okay, then we're going to go ahead and get into it. So for set 2.2, let's see what we got. Ooh, let's go ahead and we're going to go down to number 5. So we are looking at elementary matrices. So let's go over a couple rules. Elementary matrices have a little set of properties. So what are our elementary row operations again? What can we do to a matrix? Yes.
Block rows or columns.
Yes, we can swap rows or columns. So if we do that, and we end up with an elementary matrix, what happens to its determinant if you switch rows? Sir.
Or the opposite of original.
Oh, good job. Yes. So in case of elementary matrices, if you've swapped rows, then you have your determinant is -1. All right, what's another row operation we can do? Matrices. Let's see if our online folks. Let's see. Yes, Cody says we can. Yeah, we can multiply a row by a constant. So if we're dealing with elementary matrices, we know about the determinant in that instance? We multiplied a row by non-zero constant.
That factor multiplied by the determinant.
Yeah, so we multiplied, you got elementary matrices where a row is multiplied by 3, our determinant would be 3. What happens if we multiply a row by a non-zero constant and add it to another one? Yes, sir.
The determinant doesn't change.
Yeah, it's just the one. When we're talking about elementary matrices, it's just one. Okay, so let's look at this. So we've got 5. What do we think is the determinant here? Yes, sir.
-5.
Everybody agree? All right, let's check it out. Yes, the third row of I4 was multiplied by -5. So the determinant equals -5. What do you think happened to 6? What do we do to I? The identity matrix to get number 6. Yes, sir.
Still times the same row, which automatically all of them be equal to 1. So,
Oh, good job. How did you arrive at that conclusion? What do we do to I to get this E?
well, since 5 is sort of similar problems, it's still 3 by 3, so I just all them like again diagonally.
So for number 6, how did we go from the identity matrix to get that elementary matrix? Number 6. I heard you say multiply. What did you multiply?
And 1. 1 times 1.
I think we have some other suggestions. Yes?
You multiplied the top row by -5 and add it to the bottom.
Yep. So what does that mean our determinant is then for this case? Yes, sir.
1.
Yep, 1. All right, let's look at 7. What happened to your identity matrix to make it this elementary matrix? We swapped what?
2 and 3.
Yeah, we swapped 2 and 3. So what does that mean for our determinant? It means its determinant's -1. All right, let's see. Number 8. What happened there?
Times by 1/3, -1/3.
So our determinant is -1/3. If you were not told that this is an elementary matrix and you were just told this is a triangular matrix, what could you tell me about number 8?
Times the main diagonal.
Yeah, we would call this what kind of matrix? What kind of matrix is this?
Diagonal makes
Diagonal. It's also
upper and
the
lower.
upper and lower triangular. And as such, what do we know about the determinants for it?
It's gonna be equal to the main diagonal.
Yep, we multiply along that main diagonal. So we have some things there. All right, so let's see what other ones we got for this section. Let's look at. Ooh, let's look at number 9. Oh my goodness. This section introduces a new technique. Let's look what it says. It says, evaluate the determinant for number 9. Evaluate the determinant of the matrix by first reducing the matrix to row echelon form, and then using some combination of row operation and cofactor expansion. Why do they want us to get to row echelon form by doing this?
We can identify the simple processes.
So we're going to be simplifying it. Yes.
So we can have zeros under the ones in order to use cofactor expansion.
Okay. Any other reason why we'd want to get it into row echelon form? What is row echelon form? Another way to describe it. Yes.
It results in an upper triangle.
Yeah, that's an upper triangular. So then at some point you make use of your diagonal. So, okay, so this is your chance before we go to break. Let's see who can solve this one. Let's see who can do number 9. Yeah, so good job online. Natalia definitely recognized our last one where rows 2 and 3 were interchanged. Alyssa and Cody were right on it. Create those triangular matrices or an upper triangular, you bet. All right, I got Jose and Joshua and Cody and Jackson are killing it today. So we'll see who's gonna share for problem 9 here.
Want me to say the answer right now?
We'll see if someone else has calculated it. You know how you got it?
No, my God, I just hope I did the math right. It says use cofactor expansion. I didn't do that. I used the triangle. Is that allowed or no?
Yeah, so we're gonna go through it because you're gonna be doing a combo of both.
Is the triangle part of cofactor expansion?
No, the cofactor expansion is specifically by picking an entry and then calculating the determinant of the submatrix remaining. But as you like reduce your matrix down to row echelon form, then you're making use of the fact that it's then an upper triangular.
Okay.
Easy around yourself. You'll see it as I'll go through it both ways. Anybody else get it? Sir. You got it? Okay. Anybody else want to share? Who hasn't given an answer yet? Who needs more time?
Oh. I mean, stay.
I think Jose, what do you got?
33.
You got 33. Okay. All right, so problem 9 for Jose. All right, let's see how we get 33. There are 2 ways you can go about this. So let's go ahead and we'll check this out. And then we will see how this happened. Joshua, did you get that too?
Yeah, negative 33, but it's because of a sign error.
Okay, yeah, you have to keep track of that too. All kinds of stuff going on with this. It's crazy. So let's see what we have here. All right. Okay, so that's probably as large as I can make it. Okay, so for 9, we have our original matrix is 3, -6, 9, then -2, 7, -2, then 0, 1, 5. Yes? All right, so I'm putting parallel lines because I'm indicating I'm trying to solve for the determinant. Okay, so, whew. Oh my goodness, this is different. This is different than anything that you have done before. So we're doing a combination of row, and it's specifically telling us what they want us to do. So there's obviously going to be more than one way to solve for this determinant. What would be, like, if we weren't given all these directions, what would be some things that go through your mind in solving this?
Using the elementary raw operations and keeping track of what it's doing
Uh-huh.
and trying. I mean, I did the triangle. I got
Yeah.
the triangle.
So yes.
Let's pick the second and third rows because the third row is already our final form for the second row.
Oh, interesting. Another thing that could go through your mind is maybe I'll just do quickly the arrow technique. Yeah. Nothing's striking me as being super easy about this. So maybe my fastest math might be the arrow technique. Yes.
What I did was take out a common factor of 3 from the first row.
Yeah. So, but they have given us specific directions, so we're going to do it their way. So we got to go ahead and do some manipulations here. So we're going to be doing the first thing is we're going to be taking out or pulling out a 3 from that first row. So remember, as I do this, we're talking about calculating the determinants. So we have to keep track of all these determinant terms. So we're going to be looking at 3 times what? Well, then we're going to be left with 1, -2, 3, right? And then we've got, so -2, 7, -2, 0, 1, 5. So that's going to be our first move, to pull out that 3 out of the determinant. Okay, now we want to think about, okay, well, we need to go ahead and get rid of, if we're going to create this first leading 1 here, and we're going to be using our row reductions as well, we've got to get rid of that -2. So we're going to go ahead and we're going to do 2 times the first row and add it to the second row because we need to make that -2 a 0, right? So we're going to be back to our elementary row operations. Now, here's the thing. What does that do for our determinant? Anything? Does it change it in any way? Because what is our elementary row operation? We are multiplying a scalar, a non-zero scalar by one row and adding it to another. So that does nothing for a determinant, right? So that'd be effectively like multiplying this whole thing by 1. So there's no change in our determinant, right? So then we have now, what does our matrix now look like? We've got 1, -2, 3. Ooh, this becomes a 0. So what's our next term? 3. Anybody got our next term? 4. And then we got 0, 1, 5. Now, what do you notice?
Two zeros in the first column.
You could choose. This is what you'll have to do on the exam, folks. You're going to have to be paying attention to these patterns and deciding, unless the directions specifically tell you something, you're going to decide what's the most efficient way to calculate this. So you could, right here, do what? You would look at this and you would see these 2 zeros in that first column. And what would you be doing?
Cofactor expansion.
Well, you'd be looking at along what? That first column, right? So then we'd have 3 times 1. Then we'd be looking at cofactor expansion along this position. So that'd be 1 times what? The submatrix 3, 4, 1, 5, right? And then what would we get? 3 times, what's in here? So that'd be 15 minus 4, which equals 11. What's our total? 33. It'll be as quick as that. Now, they have told us, though, in the directions, they have said that we need to get to row echelon form. So this would be the quicker way of getting there, right? But since they have told us directions, we got to keep on going. So that means, what do we got to do? If we are looking at this, we got to keep going, and we need to put into row echelon form. Well,
Times by -3. Add.
what's something really quick we could even do before that?
Swap them.
Oh yeah, you could just swap them.
Yeah, we want to swap the rows. So what happens when we swap rows? What happens to our determinant? All right, so we got to add in that swap in, how it's affected the value of our determinant. And now we have 1, -2, 3. We've got 0, 1, 5, and then we've got 0, 3, 4. All right. Now, what do you think we're going to do? We got to get rid of this, right? What do we got to turn that into? 0. Okay. So we got 3, 1, -1. How would I go ahead and make that a 0?
-3 times the second row and add it to the third.
You got it. So -3 times second row, add to third. What does that happen? What happens to our determinant when we do that operation? Nothing. So it's affected it by a factor of 1. Okay, so what is our new our little 1, -2, 3. Then we got 0, 1, 5. We got 0, 0, and then what do we got?
11.
-11. Whew. All right. What's happening now? Almost there. Yeah, go ahead.
Take out a common factor of -11 from the third row.
You got it. So we've got 3, 1, -1, 1. Now we take out that -11. And we're left with 1, -2, 3, 0, 1, 5, 0, 0, 1. Now that we have it in row echelon form here, what are we taking advantage of? Now we know that the determinant of this is multiplying along the diagonal. Yes, go ahead.
Where are the extra ones coming from?
The extra ones?
Yes, you're multiplying by 1.
Yeah, I kept track of all of our different elementary row operations and how they affected the value of the determinant. So for instance, I pulled out the 3. Then if you multiply one row, add it to another, that elementary row operation affects the determinant by a factor of 1. Then if you've switched rows, it affects the value of the determinant by a -1. So you have to keep track of what you're manipulating and how that impacts your value of the determinant. So this is I put all those in there because I wanted to show you step by step how it was affected, so you kind of see with each elementary row operation. So then at this point, I think we can see that we have 3 times 1 times -1 times 1 times -11. And then we have our 1 times 1 times 1 for our diagonal. So all of that is going to, lo and behold, equal grand finale. What is it? 33. Okay. And the point of it being is you get the same answer, 33, as you did up here by a different technique. So you should get the same answer for whichever technique that you use. So if you had used the arrow technique, you should have also have gotten 33. So these should all lead you to the same answer. Okay, I think it's time for a break, right? So let us do it. We will go ahead. And all right, yeah. So Cody was getting it. Natalia, awesome. So yes, we did all of that things that you suggested. So good job. Let's see. So all right. So we're gonna break until we're gonna break until 3:50. All right. We'll see you back, folks. Lost track of time. Okay, we are back and Brandon has a good question. So Brandon, I hope you are back as well, so you'll hear the answer. Brandon says, will we have specific instructions like this one for the exam for some questions and some where we can determine the best route ourselves? Yes, you are correct with both questions. There are going to be some exam questions where I give you specific instructions so that I see that you understand the concept. And then there are going to be other questions where it's going to be up to you to figure out the fastest route to solve these things and be most efficient. And then that way you can finish in a very timely manner. So both of those, yes. So do make sure you read your exam questions carefully. Okay, so we are on to our next set of questions for our section 2.3. And so 2.3 had some other interesting concepts. There's a couple different theorems about the determinants. But towards the end, we had some interesting things where we learned some new terms. And one of them was the adjoint of A. So without looking at the screen, does anybody remember what the adjoint of A is?
Adjoint is?
Yes, the adjoint of A, yes.
The transpose of the cofactor matrix.
Oh, good job, yes. And why do we care about the adjoint?
Something to do with the determinant.
Yes, sir.
It helps us find the inverse.
Yes.
Oh, there you go. Good job. So we care about it because it will help us with solving for the inverse. Because the inverse, if you have a square invertible matrix, your inverse is equal to the adjoint of A divided by the determinant of A. So that is another way for solving for the inverse. So for the inverse, we have a couple different things that we've got going on. We've got our equation for our 2x2 matrix. Then if we have a larger matrix, we have the inversion algorithm. Now we have this other method using the adjoint to find the inverse. So you have a couple different methods here. So this one is very laborious though, as you can imagine, right? We've got to find all those cofactors and then we have to take the transpose. So probably not the most ideal method, but you should at least know it because you may very well need to use it. Here is another cool thing that this chapter section introduced, and it was Cramer's rule. So who can tell me why we care about Cramer's rule? Yes, sir.
It can be used to find the value of the unknowns.
So it is a new method for solving for your system. We learned that the inverse is very important for solving for our system. Does anybody remember that case? How can we use the inverse to solve our system? Anybody remember that from the previous chapter? I'll give you a hint. See that matrix equation, AX equals B?
What it's saying, to be honest. Like, the determinants,
Uh-huh.
like A1,
Ah, okay.
I don't know what it,
What that means?
dividing determinants.
Uh-huh, okay. So let's just go to that matrix equation AX equals B. What do we remember from our chapter 1? Yes.
The coefficient matrix times the unknown matrix is equal to the whatever's after the equal sign matrix.
So it's a really short way of representing your system, right? Now that's assuming that your coefficient matrix, let's assume that it's square. Let's assume that it's invertible. Then what can we do?
get the inverse on both sides, solve for X.
Exactly. So you can,
20.
exactly. So if A happens to be squared, it happens to be an invertible coefficient matrix, we can go ahead and solve for our unknowns X. So X would equal the inverse times B. This is yet another scenario where if you have this matrix equation and your coefficient matrix A is square and it's invertible, then you can now make use of all the determinants to go ahead and solve for your system and your unknowns. So let's just review really quickly. What is this A1, this A2, A all the way through N? Does anybody remember what is happening there? Yes.
The matrix that results when you replace a column with the answer column, with like B.
Yeah, exactly. Good job. So let's go ahead and look at this example really quickly. So do look at example 8, hint, hint. Let's see, Alejandra says, will we have to solve a whole adjoint problem on the exam? Yes, I will ask for you to go ahead and do that. Just to show that you know what that is, and that you know how to use it to solve your system, but it would only be one question. Let's see, write the solution to the system equation as a ratio of determinant. Yes, Cody, yes, it's exactly what we are doing for Cramer's rule. So here you have your system of equations. You happen to notice that your coefficient matrix is a 3 by 3, so it's square. What do you need to make sure that you do first to be able to know if Cramer's rule even applies? What is all of this contingent upon? We're going to be solving for all these different determinants, like determinant A1 over A.
Determinant of A can't be 0.
Right, because A has to be
Inverse.
invertible. Okay. So A here, this is, you always would want to go ahead and check. What's the quickest way to check if A is invertible? Or that another way of saying that would be that the determinant does not equal 0. So if you had A right here, what would you immediately do if you're given this matrix? Yes.
Check for rows or columns with zeros and for proportional.
Yep. So do we see any of that? I don't
See something. Wait. No.
Almost though, right? That was almost.
Oh, it's close. It's not.
Very close. One of them was almost proportional, but luckily it wasn't. Do we have anything to easily help us? Not so much. So what would be probably the quickest way to take the determinant of this A? Probably the arrow technique since it's a 3 by 3. Okay, so I'm going to assume that they went ahead and did that for all of these. But what they did is exactly what you all stated and what Cody was saying online. You want to go ahead and so if you're solving for x of 1, what you're doing is you're taking the determinant of A1. So how did they form A1? Well, if you look at it, it's your coefficient matrix A, except this first column has been replaced by the values of B here, 6, 30, and 8. So that would be A1 for the first column being replaced. A2, you'd notice that the second column is replaced, right? And then A3, this third column has been replaced. So once you've made those replacements, then you're taking the determinant of those matrices. And so they've gone ahead and done that, and they have formed their different ratios here and to be able to solve for their x1, x2, and x3. So let me pause here. Does everybody see that pattern with example 8? What's happening there? Any questions on that one? So this is a way to solve for your system, but it does assume that your A is a coefficient matrix that is square and is invertible. So please don't forget those assumptions. So if it's invertible, it means that its determinant does not equal 0. So you'll make those checks. The other thing that I want you to note is this is something that Cramer's rule might pop up from time to time, depending on your application. However, it's usually only used for 3 by 3s. So that's something to keep in mind. You're not going to want to do all of this work for It's very inefficient if you have large systems. So keep that. The other thing that I wanted to make sure that you also paid attention to is we keep accumulating equivalent statements. So at the end of each of your chapters, please make sure that you check these equivalent statements. So we are now to the point where we are down to G at the moment. So here, if A is an n by n matrix, so it's square, then the following statements are equivalent. So that means they all are all true, all false. So we usually want to hone in on a couple that really are very useful to us. And I have to say G is probably our most useful right now, right? Because if the determinant does not equal 0, then we know it's invertible. And then we know that we can do some different techniques. So if A is invertible, then we can use the inverse to solve our system. If we get the determinant of A does not equal 0, then we can use Cramer's rule and use all those ratios of determinants to solve our system. The other cool thing that we know also, if you look at E and F, is that we know we have a consistent system. And then we also know that we have a unique solution. So these are cool things to note. So we want to make use of these equivalent statements wherever possible. And you're going to be seeing this as a reoccurring theme.
On an exam, could I use an equivalent statement so that I don't have to show my work?
You possibly could.
Like if I was reducing a matrix
Uh-huh.
and I said, since this is true, this means that the reduced matrix is an identity matrix.
Okay.
By the equivalent statement, could I do that?
Right, you could. If you were asked to solve for the identity matrix or a reduced row echelon form of something, you could use that. But if I'm actually asking you to solve for the actual system, like you'd have to do more work, right?
Yeah.
You'd still have to solve.
It says, get this into identity matrix, you would have to get into identity matrix, right? You can't just say, oh, but.
That would be kind of creative though. If you had a matrix and you then like showed me that the determinant doesn't equal 0, then you could say, oh, well, by these equivalent statements.
You would accept that.
You're making use of the theorems. Now, if but you would want to make sure that you're following the instructions on the question. Like if I blatantly wanted you to show a certain method or solve for something specific, then no. But that would be a very creative answer. So that'd be very interesting. I have not had anybody do that yet, so I will be interested to see what you all come up with. Okay. All right. We are looking at problem 5. And these are going to be some things that you are going to be hints, some similar things you might show on the exam. This is just an example. You would want to verify, you always have to check because order matters. And we know that with multiplication, and hopefully you have proven that to yourself, that the product AB does not always equal BA. Who knows the instance when the product AB does equal BA? Did anybody make the connection of when that happens? Yes.
When a row or column in C is the result of adding a specific row or column of A and B.
Okay. I think you might be talking about the determinants, but I'm just looking at the product AB. When does it equal BA? Did anybody make that connection as you went through chapter 1, chapter 2? Does AB equal BA? When does it not matter the order? Oftentimes order matters, right? And then you can't multiply those matrices. Yes.
When they're the same size over the.
Okay, so one of the things will be that they will need to be the same size for sure. That's not the only thing though. One of the properties.
To do with a matching column.
Does AB equal BA?
No longer on.
What does it equal? Very unique situation. Let you all ponder that and see if you can come up with it next class. So ponder that question. But in any case, this is talking about determinants. So it's asking verify that the determinant AB equals the determinant of BA. And they were asking you to determine whether the equality determinant of A plus B equals the determinant of A plus the determinant of B, whether it holds or not. So that second one, the determinant of A plus B equals determinant A plus determinant B, it does not always hold. So you will need to be able to verify whether or not it does. So how would you go about doing this? If you had received exam questions like this, hint, hint, what would you do to verify this first part?
Get 2 products, get the
Yeah.
AB product and then get the BA product and then
Excellent.
do the determinant of both.
Mm-hmm.
I don't know if there's a faster way. I feel like that it's kind of the way you have to do it.
Yeah, that's how you have to do it. What would you do to make it faster for yourself on the exam? This one's a 3 by 3. You probably want to pick a 2 by 2, right? Make it real simple.
Oh, if you have the option, absolutely.
You have, yeah. So if you were to verify this on the exam, yourself, probably want to pick a simpler matrix. So definitely, what you said, you would go ahead and you'd have your matrix A or matrix B. For proof showing verifying this first left-hand side, you take the product AB first. Then you go ahead and calculate the determinants. Then on your right-hand side, you take the product BA first and then calculate its determinants. Then what would you do for this other part here? How would you go about showing that? Kind of just follow it, right? So on this left-hand side, for determinant A plus B, what would you do there? The parentheses telling you that you need to do.
You gotta add them first.
Yeah, you'd add them first, then
Determinant.
solve for your determinant.
For both determinants and add the values.
And then here, you're taking each matrix separately and calculating its determinant and then adding them. So let's go ahead and check out our solution here. So here is determinant AB. So if you multiplied AB together, you would end up with this matrix. Then you go ahead and take its determinant. What method do you think they use there? What do you guys recognize this as? Look at that math. Yes.
The arrow technique.
You got it. The arrow technique. That would be the easiest because we don't see anything useful about this. Any other way would be a lot of extra work. Here they did BA, so they multiplied BA in that order. They got this matrix. Now they're taking the determinant of it. And you will notice that they've got negative 170 for both. So that would tell you that in this case, the determinant AB equals determinant of BA, it holds. Yes? For these particular matrices. Then down below, they have determinants of A plus B. So they added up A plus B first, then took the determinant. They get negative 30. Then you'll notice below that they went ahead and took the determinant of each matrix separately. So determinant of A, they got 10. Determinant of B, they got negative 17. What's the problem here?
It doesn't match.
Negative 30 does not equal
So
negative 7, does it? So you would be able to determine that this equality does not hold for these matrices.
don't you need a matching row or column? for it?
Yes. So then you'd go back to that theorem that was up above, that A and B can't be different except for one row or column. It's up above in the,
If they had 2 of the same rows and columns, could it also work?
yeah, it can only be different by one.
only one?
Yeah, so if you look at theorem, let's see where to go. Page on it. If you look at, you look at theorem 2.3.1. So that would tie into there. So if C happened to be, result of was only differ by one row or column, then you could say that it equals determinant A plus determinant B.
Differed by 2, no. Differed by 0, no.
Yeah, that's only the way, yeah.
Only one. Okay.
Yeah, so 2 would be a no-go. Okay, so let's go and we will look at, let's look at 10. Let's see what the directions are. Use determinants to decide whether the given matrix is invertible. So if we look at 10, shout it out. What do we know?
The determinant is going to be equal to 0, so we know it's not invertible.
It's not invertible. What do we notice?
Columns of
Second columns of all zeros. Boom. We know the determinant 0 is not invertible. All right, let's look at 11. So always stare at your matrices first. See if you notice anything. Yes.
No columns,
Oh, which ones?
the first and third,
You got it. So we've got proportional columns. What do we know then?
determinant is
Determinant is 0.
the proportional,
Yes, they are. What are they proportional by?
factor of 2.
Yes.
First column,
So first column and third column for number 11. So 4 times 2 is 8. Negative 2 times 2 is negative 4. 3 times 2, 6. So want to make sure. So that's exactly what I am going to be looking for on the exam, is whether or not you remember some of these rules, right? And you make these
Oh, I see now.
these patterns. You see these patterns with your matrix because they're going to help you eliminate work. Right? If you can immediately answer a question, then you have all these other minutes to spend on your other questions, but that depends on you studying and kind of remembering some of these things we talk about. So recognizing patterns there. Okay, so let's see. Let's look at number 15. Oh boy. This is kind of similar to what we did before. But 15 says, find the values of K for which the matrix A is invertible. Remember last time we asked, okay, what were the values of lambda so that the determinant equals 0?
Can we set it to 0 and then find the interval in which it's not 0? I feel like that's got to be the way.
Very, very interesting. I like it. Does everybody hear what was said? So you can use that same strategy, but you just come to a little bit different conclusion, right? So here, 15, and hint, hint, I will probably give you some things like this on the exam because I want you to understand what it is you're calculating. So for 15, it says find the values of K for which the matrix A is invertible. So if I set the determinant equal to 0, what would I be solving for?
Where it is not invertible,
Right.
and then just exclude those in your real number.
Exactly. So you would set that equal to 0 and you'd be able to say, you know what? These are the values of K where A is not invertible, where the determinant equals 0. So that means everything else is fair game. So let's take a look at 15. Cody says, will the rules be given as theorems at the bottom of the exam like exam 1? You betcha. So you don't have to worry. So when you're studying for your exam, please review all this. I don't expect you to memorize it, but I want you to review it enough where something triggers in your mind. Oh, there's a pattern here. I can go through and I'll look at the exam material I give you to see if you can find out which rule it was. But you got to study and to know that for it to trigger that there's some pattern you should recognize. But I don't expect you to memorize it. You'll be given all that good stuff at the end of the exam like last time. Okay, so with 15, let's go ahead and check out what happened here. So we have determinant of A. We've got k minus 3 times k minus 2 minus -2 times -2. We're going to go ahead and set all that equal to 0. And we end up with our nice little equation here.
It is that bad.
And it's bad.
I was looking at him like.
It's nasty. Yes. So, when you have all of this nasty stuff, when k equals 5 minus the square root of 17 over 2, and when k equals 5 plus the square root of 17 over 2, that is when your determinant is equal to 0. And that means those are the values of k where a is not invertible. So a is invertible if k is anything else besides those two values.
The quadratic formula.
Yes. All right. So does everybody know their quadratic formula? I will put it on the exam for you so you don't have to memorize it, but it is a very useful thing to know. Just moving forward, I'm sure you'll use it again. So anybody, if you are solving for k or some other unknown, it is, if you're dealing with power of 2, your value of x is going to be equal to -b plus or minus the square root of b squared minus 4ac divided by 2a. In case anybody wants to go ahead and remember that, but I will put on the exam for you. Cody has been nice enough to put it in the chat for you if you want to go ahead and write that down. Yeah, the honor log calculator, you will not have something quite so nasty. So, but yes, you should be able to do that with your, with the help of a calculator, on-screen calculator. So between your scrap paper and your on-screen calculator, you reckon you can do it. Okay, so we have in our time left, you have a team challenge. So we'll see which teams have been studying. So you will want to go ahead and get a hold of your team at this moment. And I am going to be posting a little challenge for you. And I hope you'll find it fun because you'll be doing an encryption challenge. And inverses were used to encrypt all kinds of messages in military warfare and other scenarios before we've had our modern methods. Obviously, our modern methods have to be way more advanced because we've all cybercrime. But we used to use inverses for message encryption. So you will have your first little team challenge. So please make sure you assemble now in your teams, and you will have the last 20 minutes, and we'll have a friendly competition to see who can decode the messages the fastest, making use of what you know about inverses and determinants. I have one other quick announcement. We have learned some methods for calculating determinants and inverses. If you would like to earn extra credit, you and your team can present next time if you know of other methods for calculating these, because the textbook doesn't go over all of them, but you may have learned something else in some of your other classes. So if you'd like to share that with everyone, you can do that next time. But on with the game. I will be posting really quickly your All right, so you will find it under your chapter 2 module. I am now going to post your challenge. So you have a message, an encrypted message to decode. We'll see what you do with it.
Is it?
All right, so those of you online, you're gonna want to jump on your team channels together. That way you have private time. And those of you in class, you'll want to find your team. Yes, sir.
What is some of our teammates are online right now? How'd that work?
Yes, you'll want to contact them through your team channel. So you'll say to them, hey, I'm here in class, but I can see you online. I can chat with you online in my team channel. You know what team number you are? So you should be able to jump on your team channels.
So that's.
So everybody sees this, yes, in teams, like you have your own individual team channel. So you can hop on, if you're in team one, you would hop on the team one channel and you would be able to talk to your team one teammates if they're online.
What is that asking?
So we have two keys and three messages. Let's use the keys to encrypt or decrypt.
Yeah, but I agree with that.
What?
When you solve the matrix, we get a value, that value relates to the letter.
Diesel's kind of.
And once we have the two letters that are keys, what does that mean with?
Yeah, they got the over in
What does that mean?
Level.
And then you would hear like 5 minutes later.
Oh, I know, I was in and out. Try to.
Oh, sorry, so something like. To do code. It's a cyber criminal.
Literally no reason to draw.
Messages.
That's on.
So that'd be decrypting, which we don't have. Multiply the original message and names, their encryption key, create their own encrypted. We do the we do that one theorem, as long as the determinant is not zero, we do the one theorem. It's equal to times b. We use that theorem to get our.
I'll say encrypted.
I said that, but I said we're racing the 213. But that's what we do. Assignments. That's how we think the matrices, and then once we do that, I think we solve the matrices. 3 matrices, we solve them all, and then we get 3 letters, and I think that 3 letters is less than code.
For next job function.
But
It's not as hard as you think.
Let's save the hospital. They're counting on you.
I'm just gonna start writing things out.
The encryption. Hey. Be an incredible matrix. Okay.
This is what we use it for.
The messages.
Okay.
Everyone knows they use a matrix,
So for each message, we divide it by the value we get for the
they
key.
multiply their original messages and.
Yeah, but we're not actually dividing.
A equals Z.
We're doing matrix inverse, so that's not division.
Yeah, but I mean like. The matrix you get is the kernel. That's a value. That's the end.
They try to.
Divide that by
Okay.
One goes out to what but we all agree that X equals B is what we're gonna obviously do. So it's gonna be K. And we get the Z. And then.
Yeah.
We need to go through the. So we're given E and we're just given K. We're not given that to define.
Yes, and we find by doing,
You get the inverse. You get the inverse.
Yeah.
Really annoying method, but it's also,
What's that little thing?
gosh, oh, I know what you're talking about now.
yeah.
Formula. I remember.
Oh, no, I'm talking about the given formula. Yeah, so the.
You want to know the determinant formula to get inverse, because A equals inverse, so the one determinant A of the jointed A. Or we could honestly just do echelon form. Get the I on the other side,
She said how to do this.
just use that. Oh, wait, they're not.
We need to find which key.
There will be no embers.
Which of the ones, which of these two are?
No, because K is a square matrix, because it has to have numbers.
Yeah, the keys.
It's indeterminate.
These have to be squares and numbers.
Oh, good, good.
Should have two screens, it's painful.
Okay.
But it. You just. That's how you get here.
It's a key. Yeah. Oh, yeah.
Alright, Joe.
I'm doing one.
You want to take this up, right?
I wanna do one.
This team card.
Yeah, no, but yeah, what you want to say?
I'll let you guys.
I want to see if I can try it, or if I can add you for team 5.
Yeah, I got it.
Read, there's no key 3.
Wait, you guys are doing. We could just.
That's a picture of our word.
I'm not for the key.
Well, I'm gonna do key 1. You said all this.
Let's think of them.
Yes. First, just get out. Okay, I see.
We're still gonna, I can hear myself. This is terrible.
Is there a simple formula?
Oh, me and you're gonna echo the whole time.
I'm muted.
You're muted.
I'm muted, so I don't.
You should just use AI.
Yeah.
No, not.
No. Yeah. No, I don't think. How do you look on it?
Only the teacher knows what I'm saying.
Oh my God, I got. It's there right now.
Oh, is it because you're.
Have these to appear. If I'm verbal.
Yes, we just need to use.
Because you're, he was using your. Change it to.
Hello.
Yeah.
Okay.
You start doing this.
Taking the first.
Looking for the first two or first lines. Is this stop?
We're gonna use that, I guess, to decode.
He was having a teacher section.
It's in Canvas? Yes, it's in the chapter 2 module.
Oh, okay.
So it's under the assignments.
Oh, yeah, I see.
Yeah.
Has anyone got the inverse matrix yet? Fractions.
First type is just.
It's not for the second.
If it's in the
Do
region,
this the first time.
which one to choose? First two. Yes. To different
Well, the key, I'm a key under right now.
instance, decided tools have used the matrix encryption design.
CJ, I keep what?
What is
Quick question. What's up? There's 5 problems in this one, right? And well, there's 2 keys and then 3 message, right? So if there's encryption key 1, encryption key 2,
We've determined which key to use.
and then you got encryption message 1, 2, and 3. Should be encryption key 3 as well, or no?
No, we have to use K and E.
You need to do fractions.
We won't find out.
We're just getting a code that we can round at the end.
Scroll down. Says A times M equals E. So the key times M equals.
I think they're asking, I think that's.
Yeah, K one.
Sorry.
If you reverse it and do, see message equals the inverse of K. So
Randy, you got the same thing.
inverse of the key, and then multiply it to the message.
Randy, you got K one's not invertible, right?
Yeah, I think so.
Pretty sure.
Okay, you got the same thing. Yeah. And K two.
Which K two is inverse of one, K it's not, so it's an inverse K two. Which. I don't see.
I guess we just start. Um,
Perfect. Without using to find the inverse. I think we just put it in the nature, the ID.
Like the
Kidding me? But you just don't feel. Because you keep on splashing one. Not getting that.
Is anyone else getting its non-vertical?
And inverse thing this.
that.
At least one.
Got that too. It's also doing. It's like bad. The second row to the president. I kind of trust you because you're not using decimals. Same mistake